Okay, it's 30 past. Um, Maybe just as a comment beforehand, I will put up homework 5 probably later tonight. I assume you'll understand if I want to take a little longer to proofread it after things went with homework 4. So just make sure I get all my assumptions right. Um, all right. So last time we were talking about fiber product. So recall fiber product is the unique scheme that has a map to X to Y such that the map to Z, when I compose these two, gives me the same thing. This diagram commutes. And if I have any other W with maps into X, Y, and Z that make everything commute, there's a map of W into the fiber product. Well, writing in the map from W to Z emphasizes that there's one map from W to Z, which is the same either way, right? So, I mean, right, what I'm writing here is the definition of the limit of this diagram. All right, so this is a really important geometric operation. We discussed last time that sort of lets us generalize a lot of notions we've already talked about, intersecting open subschemes or closed subschemes, um, various other things. Um, so yeah, now I'm sort of like, what are the things we haven't? Just want to make sure I don't miss anything. Um, all right. So one important example, which just kind of emphasizes how weird fiber product is, we sort of talked about this a little bit on Monday and then didn't have a chance to come back to it, is you can get this kind of strange behavior, like if I take spec C, 2 copies of spec C, and cross them over spec R, then what I get is the union of 2 copies of spec C. And the kind of picture you should have for how this works is roughly that spec C is a double cover of spec R, right? As we talked about, field extensions are kind of, you can think of them as covers. In this case, it's degree 2. So you should think about a picture like the unique double cover of the circle, and think about what would happen if you took the fiber product of this guy with itself. Um, so I would get a quadruple cover. So every point on the circle would have 4 preimages. And what would happen was I went around the circle. Well, here I have 2 preimages, and as I go around the circle, they switch. So sort of in both of these factors, it would switch. As I went around the circle, I would connect up to this guy. And as I went around the circle again, I would connect up here. Similarly here. Okay, it's maybe not so easy to see what happens, but you get 2 copies of this guy. So this is sort of reflecting a geometric thing that happens with these double covers. Um, but of course, this is a purely algebraic statement. This is just about what happens when you take the tensor product of these rings. Um, you right, what you get is so think about what the statement with topological covers is. It's that you get the product of the degrees, but you get a disconnected cover. right? If you're thinking about topological covers, the way to think about topological covers is they correspond to finite sets with an action of phi 1. And what I'm doing is I'm taking the product of those two finite sets. And the point is somehow a field extension is like a connected cover. So more generally, a sum of field extensions would be like a disconnected cover. Yeah. No, there's no ramification here. Right, right, ramification would be something like a branched cover. Okay, I think this is just a helpful example to think about. More generally, one of the important constructions that makes more sense now that we have fiber product is if I have a map from X to Z, and I have a point in Z, I want to think about the fiber over that point. And while you can think about the literal fiber of that point in scheme as a topological space, but it's not obvious how to think about that as a scheme, especially if the point isn't closed. So the correct definition of the fiber is I have Z, I think of a point. So if I have some little z in here, I can think of that as a map from spec of the residue field. So remember, this is the local ring at Z mod its maximal idea. All right, and then I can take the fiber product of these two things. And this is the usual sort of notion of the fiber over the point Z. I get a scheme over this residue field that maps in here. And of course, this doesn't actually have to correspond to a point of Z as a underlying topological space, right? It could be a K point for some field K. Or generally, given a K point or a field. So what does that mean? That means a hum from spec of K into Z. I can again form this fiber product. So actually, that's an example of what I'm doing here. I'm thinking of the unique C point of spec R, and I'm taking the fiber of spec C mapping to spec R over that point. And I'm getting two copies. Yeah. Yeah, this is sort of the most natural choice. And maybe I shouldn't put Z here, whatever, I'll put alpha, where alpha is the name of this from spec K into Z. All right, so for example, a common thing you want to look at is the generic fiber. Right, so that means that, in particular, if Z is integral, right, there's going to be a generic point, and I can look at the spectrum of the residue field of the generic point, which is just the function field of Z, right? And that has a natural map that sends the unique point here to the generic point here. The common thing I'll want to do is look at the fiber over this generic. So this is sort of a weird thing because it's not actually like smaller than x, right? This guy is going, let's, for the sake of argument, say x is integral. This guy is going to have a generic point, which is the same as the generic point of x. But I'm sort of throwing all the information about what happens over non-generic points of z. So for example, right, I might look at the ring homomorphism from polynomials in some variable x to polynomials in some variable y. That sends x to y squared, right? And this gives me a map of affine schemes, which is generically 2 to 1. So think about like the complex case. Here I have the complex plane. And when I do the squaring map, well, what am I doing? I'm sort of kind of cutting the complex plane along a line, and then I'm sort of doing a double cover over here. So if I go around the unit circle here, I go around the unit circle twice here. And then there's sort of a bad point where the fiber is not reduced. So what would happen if I take the fiber over a closed point here? Let me just sort of emphasize that. What does that mean? That means, let's for now say K is an algebraically closed field. There's nothing that special about it, but it sort of makes this discussion a little bit easier. So a point of this guy is going to correspond to a homomorphism from K of x to K. So x is going to get sent to some scalar A. And if I didn't have an algebraically closed field, I would just be looking at a field extension. More generally, I would just be looking at all the different maximal ideals of this polynomial ring, right? So then the fiber, let me really draw this picture. I have A1 mapping to A1. And here I have the point A. Well, what happens here when I take the fiber? So I'm taking K of Y and I'm tensoring it over K of X with K. So I'm setting Y squared to be the scalar. So this is spec of K of Y mod Y squared minus A. So if K is an algebraically closed field, then that just means if A has 2 distinct square roots, I get 2 copies of K. But of course, there are cases where there aren't 2 distinct square roots. There's characteristic 2, and there's also A equals 0. So I could also get spec of K of Y minus Y minus the square root of A squared. Square root of A is equal to minus the square root of A. Right, so this scheme theoretic fiber is sort of telling us about what the preimages look like, but it's remembering, oh, the preimage of this point, it's a fat point. It's not the reduced scheme structure on the unique preimage. I'm supposed to have 2 preimages, and this sort of remembers that. All right, so what would it mean to take the generic point, right? There's another point of this scheme, which is the generic point. And in sort of this schema, that corresponds to the ring homomorphism. K of x maps into the rational functions on x. So taking the scheme theoretic fiber would mean taking rational functions in x and then hence adjoining y and modding out by y squared minus x. And this is a field extension, right? In here, kx doesn't have a square root. So I'm seeing an interesting non-split field extension, which I could also get here if my k wasn't algebraically closed, right? I could have an x that has two distinct square roots in a field extension, and then I would be getting spec of that field extension. So this is the generic spec of this guy is the generic fiber. So this sort of field extension thing is telling me that I have two pre-images, but I can't, in a polynomial way, sort of separate those two pre-images, right? The problem is exactly that taking the square root of x isn't a polynomial operation. So even though if I'm thinking about like manifolds, I understand kind of, generically, I have two distinct pre-images. I can't kind of using algebra distinguish, say which one is better than the other. Okay, great. Do. Vakil has, I think at various points made this point, but let me mention it again. The generic fiber is an actual scheme with which you can, talk about its scheme properties or lack of scheme properties. The general fiber means the fibers over a dense open subset. So I might make a statement like the general fiber of this map is connected. And that means something subtly different from saying the generic fiber of this map is connected. And actually, you see this here. This is a connected scheme, right? It only has one point. As a topological space, it's connected, right? But if I look at the fiber over a generic point, at least if my characteristic isn't 2, that fiber isn't connected. There are two things in it. So I would say the generic fiber is connected. The general fiber is not. All right. Any questions? The generic fiber is a scheme. The general fiber means that when I say X is true of the general fiber, I mean X is true of the fibers over an open dense subset. Yes, right. The way this is defined, it's obvious. Yeah, part of the point of defining the fiber this way is it makes it clear what the scheme structure on it is, right? That if you're going to think about fibers in the topological sense here, right, you could take the pre-images of a point, but even if that is a closed subscheme, it might not be obvious which scheme structure to take on it, right? And for example, here, if I look at the fiber over the generic point, that's not a closed subscheme or an open subscheme. So in what sense do I get to talk about a scheme structure on it? In order to define that, I have to do fiber product. Yeah. No, a dense open subject, right? I mean, the point is this is sort of something we often talk about in mathematics of, generically I have this behavior, or I should maybe say generally, right? And one often runs into trouble of needing to say exactly what does generic mean, right? Generic usually means, oh, something happens over an open dense subset. But what precisely do you mean by that? Okay, cool. So earlier in the book, Vakil had made this definition of a reasonable property, where he was sort of cheating a little bit. A reasonable property of a morphism of schemes. Mm-hmm. Yeah. I mean, if it were independent of the open dense subset, that would just be saying it happens at every point. And there wouldn't be any point in discussing it, right? So generally means most of the time, but there are some exceptions. All right. A reasonable property of a morphism of schemes. He was kind of cheating because he defined this before fiber product, but what this should be is invariant under composition, base change. So this is where he was cheating. He started talking about base change without having defined fiber product. But this is where I want to sort of emphasize, right? Base change also means fiber product, but it means thinking about fiber product a slightly different way. This is sort of thinking about if I have the morphism of schemes from X to Z, and I want to know whether it has some property, then I want to think about, well, if I do a base change, which just means take the fiber product of X with some Y over Z, does this new map alpha have the same property, independent of what properties the map from Y to Z had? So this is what invariance under base change means. It means that if alpha has P, then for all beta, alpha prime has P. So base change is just sort of emphasizing that I want to think about the analogy between these maps, not specifically about this space. So for example, when I'm taking a fiber, right, a property that's invariant under base change, well, if this family has it, then the fiber will have it as a scheme over this residue field. And then finally, it has to be it's not invariant under, but has a locality on the target. So it's something where I can take the target, divide it up into open subsets, and check it separately on those open subsets. Now, I'm really, I don't need to phrase this in terms of base change, but this is sort of, I really secretly am using base change. I'm using that if I have Z and then I have an open cover of Z, well, then I have this base change. That's just the pre-image of UI under the map. But locality on the target is going the other way, right? It's saying I want to check if alpha has this property. And I look at these base changed guys, the restrictions, these open subsets. So if AI has P for all I, then A has P. So it's a sort of restricted converse to this base change property. It's saying, well, if certain base changes, the ones corresponding to an open cover, have this property, then my morphism has it. Okay. So lots of types of morphisms have these kind of properties. So for example, quasi-compact, separated, affine. Should emphasize here, I mean being an affine morphism, a morphism where the preimages of affine open subschemes are affine again. Finite height, if you put locally in front of all of these. So there are lots of sort of good sets of properties like this. I should mention there are some other properties that don't behave this way. So we sort of saw some problems here. For example, being connected as a subscheme is not invariant under base change. Right? You can have, or sorry, having connected fibers. Lots of interesting properties don't, though. Um, so examples of interesting properties that don't have this are being injective, right, as a map on the underlying sets. Well, we already saw that here, right? The map from spec C to spec R is a bijection on the underlying points. And if I base change it, it becomes a 2-to-1 map, right? The fact that I had different fields on these points was somehow remembering it's not really an injective map, sort of secretly not. Connected fibers, well, that's another example. Irreducible fibers, reduced fibers. There's sort of all sorts of problems you can have with these guys. Being open as a map, being closed as a map, etc. All right, so we won't talk a lot about how these fail. They mostly come from this kind of, doing weird, like non-algebraically closed fields, right? You could sort of imagine how you would get, well, we already saw this with the C, but there are lots of other ones where, you have some set of equations, set of real solutions is connected, but you go to complex solutions and it becomes not connected. Because of this issue, there are some common usages around this. So we call something universally P if it's always P after base change. So for example, you might hear about universally closed universally closed maps, universally open maps, this sort of thing. So sometimes you can prove that. This is one of these, you often have this when some property isn't preserved under some sort of operation like base change, always becomes, well, was that property really the right notion? Should I have come up with a different one? So universally P sort of solves this. Yeah. I mean, I'm sure there are ones that aren't closed under composition. But like connected fibers should be okay under composition, for example, right? Like if you have a map of topological spaces with connected fibers, right? And I think the thing that's true, at least for connected and irreducible fibers, is like those are things which work if you are working in the category of topological spaces. But because of this kind of behavior around, going from spec R to spec C, you can run into problems with them. So, I mean, right, these ones that are some statement about the fibers, they're obviously local on the target. And I think most of them are do fine under composition. Basically, if you, I mean, maybe not reduced, I'm not totally sure. If you have a map to something irreducible where the fibers are irreducible, the total space is going to be irreducible as well. Right? That's basically what you're using. If you have a map to something connected where the fibers are all connected, the total space is going to be connected as well. So it's really base change is sort of the most subtle thing. Another thing which will come up often is things which are geometrically P. So you'll hear this with like geometrically connected, geometrically irreducible, geometrically normal, etc. Oh yeah, normal is another one of these. Well, no, it's more that the definition of normal map is kind of subtle. So this means P after base change to algebraically closed fields. So the geometric idea here is, over an algebraically closed field, sort of geometry actually works the way you expect it to. And you can get these kind of deceptive cases where you look over some non-algebraically closed field and it looks like something's connected, but when you do the base change, it becomes disconnected, as in this example I keep referring back to. Yeah. So yes, open and closed embeddings are also examples here. We defined them locally on the target. I mean, you're an open subset if and only if your intersection with every open subset is open in the subspace topology, right? So we, especially closed embedding, we like literally defined in a way that's local on the base. I mean, I think the correct answer is, as always, the affine communication lemma. All right. Any question? How am I doing? Still got a little bit of time. Great. Well, fiber product, it's one of these operations where you'll get more used to it as we think about it. Not offhand. I mean, right, there's an obvious implication one way. If you're universally P, then you're geometrically P. Yeah, I don't know offhand. I know that I sometimes see this thing about, oh, assume such and such is geometrically connected, yada, yada. So, this is mostly just so that if you see these words, you know what they're trying to get at. I mean, so I think the idea here is that, like, I mean, there are much worse base changes out there. You can do base changes by really horrible maps that do something terrible to something. Whereas this is just saying that, like, the fibers over points for algebraically closed fields have this property. All right, great. So since we want to think about everything in a relative way, one of the sort of useful tricks now is there's a morphism that actually controls a lot of the structure of a morphism, since I never want to think about a kind of scheme on its own. I always want to think about a morphism. But a very common thing we want to consider is the diagonal map. So this is if I have X mapping to Y, I can look at a second copy of X mapping to Y. And of course, if I put X here, I can map that to X and map that to X by the identity. And of course, this diagram commutes. So I obtain a map from X to X times X over Y. And of course, the way you want to think about this is that it sends, a point X to X comma X. But you have to sort of remember that, the definition of fiber product here is a little bit weirder. So you do have to be a little more careful about that, but this is sort of the picture you should have in your head of what this map is. Okay, so there's some more, general discussion of this guy in Vauquil. So in particular, he sort of makes this definition. We say that this morphism from X to Y has the property delta P for some property P if the diagonal map X going via the diagonal into X times Y as P. So for example, we had defined this notion of a quasi-separated map, kind of horrible. It's a scheme where quasi-compact open subsets have quasi-compact intersection. But if I sort of think about what that means in terms of the diagonal, right, that means I take a quasi-compact open subset of X, I take another quasi-compact open subset of this copy of X, and the pre-image of that in here is going to be the intersection of those subsets. So for example, X to Y is quasi-separated if the diagonal from X to X is quasi-compact. All right, and I'll just note, Vauquil proves as a theorem if P is reasonable, then delta P is reasonable. So this is one good reason to sort of try to describe properties of schemes this way, because then you can sort of spare yourself the trouble checking that it satisfies these properties of base change and locality. Yeah. Yep, that was literally the next thing I was going to say. So, of course, we know and have emphasized a lot that spec as a topological space is not Hausdorff. But we also know that, schemes, when you think about them as like topological spaces over C, right? If you take the C points of a polynomial equation, think of that as a subset of C to the n with the usual topology. That's almost always, that is always a Hausdorff space because it's a closed subset of Hausdorff space. And so somehow we're obviously using the wrong kind of notion of Hausdorff. So what is the problem? Yes, indeed, recall that X is Hausdorff if X mapping via the diagonal into X cross X is a closed embedding. So somehow the reason that the topological space structure on a scheme is almost never Hausdorff is that the product topology on X cross X is totally the wrong thing to look at. And well, now we know that because we have the right definition of the product of schemes, and it doesn't even give me the Cartesian product as a set. But even if I only think about that part of it, it gives me a totally different topology, right? Even if I'm only thinking about the complex points, well, then at least as sets, it's true that A1 times A1 is A2. But the open subsets of the product topology here are the ones where I remove finitely many horizontal or vertical lines. I can't see any of the other open subsets that come from removing the zero sets of an interesting two-variable polynomial. So somehow this non-Hausdorffness, it comes from thinking about the wrong topology on the product. So the right generalization of Hausdorff, which again, for weird historical reasons, we don't call Hausdorff, call separated. So a morphism from X to Y is separated if the diagonal from X into this fiber product is a closed embedding. And the reason that this is not the same as asking whether the underlying space is Hausdorff has to do with thinking about a totally different notion of closed here from the product topology. Right. Generally, right. I mean, if you think about what I just said about this, the product of, let's just say, the C points of A1 and A1, right? The image of X of the diagonal isn't even a locally closed subset, right? So in any topological space, the image of the diagonal is always locally closed. And similarly here, the image of the diagonal is always locally closed. So I should maybe say the diagonal is always a locally closed embedding. And the way we can see this is there's a very important class of separated schemes, which is almost every single one we've ever thought about. Not quite literally all of them, but basically any reasonable one we've thought about. So this is sort of a reasonableness property that almost always you want to use, but every once in a while, you, for whatever weird reason, do want to think about a scheme that isn't separated. So the sort of first reasonability is that spec of A is always separated. Um, And I shouldn't be talking about a scheme on its own. I should be talking about morphism. So spec A over spec B for any B mapping to A. So if I were to say, this scheme is separated, I would mean that the morphism to spec Z was separated. But we can make a more general statement, which is just any time we have a map between affine schemes, that's a separated. And the proof is pretty easy. What's the diagonal? Right? The fiber product of an affine scheme with itself over another affine scheme is going to be affine. So this is my X, this is my Y. If I take this fiber product, that's spec of A tensor B over A. What's the diagonal map? So it's a map from X into here, where if I do the either projection to X, I should get the identity, right? And the two projections of X correspond to the two maps of A into here by including into the left factor or the right factor. So the homomorphism to A, so I need a homomorphism from A tensor A to A, such that when I compose with the inclusion of the left or right factor, I get the identity. There's only one possibility here, that this has to be A1 tensor A2 maps to A1 times A2. Right? You can sort of see this has to be right, kind of thinking geometrically about what would it mean to take functions on here and then restrict them to the diagonal, right? The left copy of X and the right copy of X both map to the diagonal by the identity. So just taking these functions and thinking about them as single functions on X, but you can also sort of carefully think through the universal properties. All right. So this is a surjective map. Since A over B with A, spec A is surjective. Well, this is a closed embedding. Remember, we defined a closed embedding to be an affine map that locally looks like the morphism of schemes induced by a surjective map of rings. Oh, sorry, yeah, I shouldn't have said, right, since the map of rings is surjective. Yeah. The diagonal is a closed embedding. And that's an affine local property. So an affine scheme, it just means I have to check it globally. It comes from a surjective map of rings. Okay, great. And you can check that what's the kernel? The kernel is the ideal generated by X tensor 1 minus 1 tensor X for all X in A. Okay, cool. So all affine schemes are separated. That's great. So what are some examples of non-separated schemes? I'm basically out of time. But let me just mention, we have seen examples of non-separated schemes, but in real life, you almost only encounter them as an example to explain why you have to check that schemes are separated, which is this usual story about I take two copies of A1, and then I can glue them together on A1 minus a point. So always what I have to be doing if I'm going to get something non-separated, well, it has to be glued together out of affine open subsets. And I have to be doing one of these stupid things where I take two affine open subsets and I take, sort of 2 points that are the limits of something, and I glue together all the things that are limiting to it, and then I don't glue the points together. This is sort of how you come up with separated subschemes and non-separated schemes. So mostly this is just something where we'll add this as a hypothesis when we want something to be reasonable. There's this whole discussion about like some people call non-separated schemes pre-schemes because it's so dumb to try to consider them, but since a fair number of theorems work for non-separated schemes, people tend to leave them in the definition of schemes. All right, time, so we'll talk about this more on Friday.